In this video, I'm going to cover with another topic of engineering mechanics, that is curvilinear motion, which falls under kinematics. So throughout the video, I'll be talking about the most important and required subtopics as follows: curvilinear motion. Firstly, we will see its definition, how acceleration, velocity, and position is represented in curvilinear motion. Meanwhile, we will see its coordinates, rectangular coordinates and polar coordinates, how both velocity, acceleration, and its position are represented and how they differ. So in the end of video, I'll be solving some questions related to rectangular coordinates and polar coordinates. So let's understand what exactly is curvilinear motion. How do we define curvilinear motion? How do we analyze curvilinear motion? So here I have an image. I'll be explaining it. So what exactly is curvilinear motion? When a particle, or let's say object, moving along a curve, its motion is said to be curvilinear. Curvilinear motion occurs when an object follows a non-linear, curved trajectory through space is considered as curvilinear motion. For real examples, I have taken rotation of Earth, where you can see here the movement of Earth in a circular path in a curved position. So how do we consider the rotation of Earth as curvilinear motion? So basically, the Earth rotation is curvilinear motion because points on its surface follows curved paths. You can see the curved paths as the planet spins around its axis. Although the Earth rotates in a near circle, the motion is curvilinear due to the continuous change in direction of points on the spherical surface. So next slide, I'll be talking about how do we represent velocity, acceleration, and position in curvilinear motion. So let's talk about how position, velocity, and acceleration are represented in a curvilinear motion. So for example, I've taken a circle here. You can see a circle with the coordinates x, y, and z. So from this origin to this P, P is nothing but a position of an object, position of a circle, or position of a curvilinear motion. You can say anything. So if I consider my position P here, if I consider from this origin to this P position here, my position will be represented by a vector, that is r bar. So again, if I consider my point here, my vector will be here, which is r bar dash. So the distance between P to P is the change in position will be represented by delta r. So I can write as position delta r, which is nothing but position change, equals to r bar dash minus r bar. So this will give me the position of a object in a curvilinear motion. So let's talk about velocity. So what is velocity? Velocity is nothing but change in position divided by change in time. From P to P, the change of position to time taken from T1 to T2. But if my time is equal to 0, then I'll have my velocity equals to limit time taken is equals to 0, then delta r by delta t, which is change in position divided by change in time, equals to derivative will be my change in displacement divided by change in time. So let's talk about acceleration now. So let's talk about acceleration. So here image I've taken from the previous slide only, with the coordinates x and y. Here is my vector, that is r bar. This is my position, this is my velocity, and this is acceleration. So what is acceleration? Acceleration is nothing but a change in velocity divided by change in time. But if my time again is equals to 0, then I have my acceleration equals to limit change in time equals to 0 delta v by delta t, that is change in velocity divided by change in time, then my acceleration will be instantaneous. That will be my dv by dt. So in previous slide, I have explained about how acceleration, velocity, and position are represented in curvilinear motion. How can we analyze curvilinear motion? What is the concept of curvilinear motion? So in this slide, I am going to explain about rectangular coordinate, which is a coordinate of curvilinear motion. So here I have taken an image. You can see here I have taken an image with x, y, z coordinates with a curved path. Here you can see the curved path, and I have given a certain position which is px comma y comma z, which will be representing the position of this x, y, and z coordinate system with the origin from here. So next slide is I will be explaining about vector. So I have explained about what is vector. Vector is nothing but it is a vector that will be representing the distance, or I can say it will be giving you the position of a object here. So I have my object at a certain point, which is P, x comma y comma z, where I have my x-axis, y-axis, and z-axis. So I can write my x equals to xi cap, y equals to yj cap, and z equals to I cap, which are nothing but the components of each axis with the origin O. So I can represent R. My position equals to xi plus yj plus zk, which is nothing but it will be giving you the position of a object at certain point. So RT is nothing but a function of time. Position components are x, y, and z, and x, y, and z are also function of time. So here I can write my equation as r equals to position equals to r vector equals to xi plus yj plus zk, which are nothing but the components of the axis, which will be giving you the location, which will be providing you the location of the object at certain location. So I can write my delta r equals to, which is the distance between this first position of a object to another position of object, which is P and P prime with certain displacement with certain distance. I can represent this distance from P to PR prime equals to delta R. Delta R is nothing but it will give me the distance from P to P prime. So I can write my R dash minus R. R dash is nothing but old position of the location minus new position of the location, which will be giving me the distance of these two objects. So let's talk about velocity. What is velocity? Velocity is nothing but change in displacement divided by change in time. So I can write my velocity equals to rate of change of displacement divided by rate of change of time. But if the time given, if the time taken by P to P prime is 0, then I will have my velocity equals to limit, that will be my delta t equals to 0, that will be my delta r by delta t, which is the rate in change of displacement or rate of change in velocity divided by rate of change of time taken. So let's talk about velocity. What is velocity? Velocity is nothing but rate of change of position divided by rate of time. So I can represent my coordinates like this: x, y, and z with the origin here, with a curved path here, with a certain position here, and it's representing a velocity with a vector r. So I can write my velocity equals to dr by dt, which is rate in position divided by rate in time. So I can also write as dx by dti, which is the components of x-axis I can write here with the components of x-axis I plus dy by dtj plus dz divided by dtk, which are also a components of their axis respectively. So I can write as x dot I plus y dot j plus z dot k, which dot represents specific for time derivative. So my final velocity I can write it as v equals to vxi plus vyj plus vzk. X and y and z are nothing but the velocity components. in this question, we need the speed of a truck of magnitude of acceleration when it moves 10 meter. You can see that we already have given the radius. Also the velocity, that is velocity equals to 4 meter per second, and also the acceleration, that is 0.05 meter per second square. So determine its speed and the magnitude of its acceleration when it has moved as equals to 10 meter. So I can write my VdV equals to AdS. Taking the interval of this equation for velocity, we need to think upper and lower. We need to think upper and lower box of interval. That is, it starts from 0 to 4 meter per second square. Velocity starts from 0 to 4 meter per second square, and the distance starts from 0 to 10 meters. So I will have my 0.05 ds. So velocity v square divided by 2 minus 8 equals to 2.5, and my velocity will be velocity equals to 4.58 meter per second. So now it's simple matter of plugging velocity and radius in normal acceleration equation. So I can have my En equals to v square divided by p, which is the rate of change of velocity divided by time taken. So En equals to my velocity I found was 4.58 square divided by 50. So the normal acceleration would be An equals to 0.42 meter per second square. So meanwhile we have to find the tangential acceleration too. So I can have my v dot equals to at equals to 0.05 and 10, which is the tangential acceleration allowed to found. All we need to do is substitute this 10 meter, which gives us tangential. So I can have at equals to 0.5 meter per second square. Now we need to find the magnitude of its acceleration when it moves to s equals to 10 meter. So I can have my magnitude equation as E equals to root under an square plus at square, where A equals to my 0.42 decimeter per square plus 0.52. So I can have my magnitude as A equals to 0.65 meter per second square. So now let us understand its coordinates and some parameters associated with polar coordinates. Suppose if this is your x-axis and y-axis with a vector r vector, where the object here, which is P, position of the object P, and a theta angle. So what is r vector? R vector is nothing but a position vector. This is a position vector will be representing you the position of an object at x, y plane. Here, if P moves in the plane only, two-dimensional motion, so theta is angle made by R vector with a positive direction x-axis in the anti-clockwise sense. So mod r vector equals to is nothing but the distance of point P, from the origin here. So I can write as r and theta are the plane polar coordinates. So you have already understood this portion, which are my x with the I components and y with the j components. You have understood this vector also. What is vector? Vector will be providing you the position, location, or a distance from the origin, and this theta is made by this r vector. So let's take it further. So from here, this position, I take a direction with the r cap, which will be my radial direction. So I can represent my x as this x-axis as r cos theta, and my y equals to r sin theta. So for this portion, this r cap, I can write my x-axis as cos theta I cap plus my y-axis as sin theta j cap. Meanwhile, for this angle theta cap, this is nothing but my transverse direction. So here my x-axis will be negative, so will be my sine theta, and my y-axis will be my cos theta. So I can represent my q cap equals to, since the x-axis is negative, so I'll be taking minus sine theta I cap plus cos theta j cap. So now let's talk about velocity. Velocity is nothing but rate of change of position divided by rate of change in time. So here I've taken x, y with a vector r, position p with a transverse and radial direction with a theta angle. So velocity equals to dr divided by dt, which is r dash equals to rate at which distance r is changing. So r bar equals to r cap, where velocity will be my r cap dr by dt plus r dr r cap divided by dt will be my r dot r cap plus r cap dot will be my derivation. So I can represent my r cap equals to cos theta I cap plus sin theta j cap equals to r cap dot equals to this will be my differentiated, so minus sin theta dot I cap plus cos theta dot j cap. So I can write as again r cap dot equals to theta dot, which we took as a common. So now we have minus sin theta I cap derivation of cos plus cos theta j cap, and will be my theta dot theta cap will be my omega theta cap. So velocity finally I can define as r dot r cap plus r omega q cap in polar coordinates. So modulus of v velocity equals to root under r square, r dot square plus r omega square. So acceleration in plane polar coordinates, acceleration is nothing but the rate of change in displacement divided by rate of change in time, or can I say rate of change in displacement divided by rate of change in time. So acceleration equals to dv by dt equals to d dt r dot r cap plus r omega theta cap. So I can write as r dot r cap dot plus r double dot, which is like second derivative of r cap plus omega theta cap r dot plus r theta cap w omega dot plus r omega theta cap dot. So I can write finally as r cap dot, it will be my omega dot theta cap equals to omega theta cap. So theta cap will be my minus sine theta I cap plus cos theta j cap, which will be my theta cap equals to minus cos theta cap I cap minus sine theta and my j cap. So minus omega cos theta I cap plus sine theta j cap will be my minus omega r cap. So here you can see I can write as acceleration equals to r dot omega theta cap plus r double derivative r cap plus omega r dot theta cap plus omega r theta cap plus r omega minus omega r cap will be r double derivative minus the omega square r into r cap plus omega r plus 2 omega r dot and theta cap. So acceleration finally will be r double derivation minus omega square r into r cap plus alpha r plus 2 omega theta and theta cap. So r minus omega square r is nothing but linear acceleration in radial direction due to change in radial speed. So it's a linear acceleration which will be in a radial direction. It occurs with the radial speed. So this omega square r minus omega square r is centripetal acceleration. Alpha r is my linear acceleration in tangential direction, and 2 omega theta is my console acceleration, which will be my transverse. So v equals to r dot, which is like derivation of dt, which is rate of change in distance, and r dot symbolize u equals to radial speed. And in this question, I've got a pin P that's going around the curve here. It's a pinpoint P going around a curve, and it's defined by R here. It's defined by R, and R equals to 4 sine 2 theta. Now I've got the slotted that's pushing around if this thing is rotating. If this thing is rotating with an angular velocity of 1.5 radius per second, I need to figure out the exact acceleration of this little peg, when theta is equals to 60. So let's start by step. So if I have r equals to 4 sine theta, I'll have my r derivative of r dot equals to derivative of this 8 and this inside ka cos 2 theta dot feet per second. So double derivative of r is r double dot equals to 8 this cos theta and minus again this 2 sine 2 theta dot square feet per second square. So I have my r dot and r double dot. So theta dot already is given 1.5 radius per second and theta double dot is 0, and angle is given theta equals to 60 degree. So let's find r dot and r double dot values. So if my r theta minus 60, if I plug this 60 here, I'll have my derivative of this as this 4 sine, and 2 into 60 is 120 equals to 3.464 feet. If I take another r dot derivative of r again, I have my derivative of this 8 cos 120, and r dot is my 1.5 radius, so I've taken this here equals to minus 6 feet per second. So if r double dot theta equals to 60 degree, then I can have my 8 theta double dot is 0 minus 2 sine 120 1.5 square equals to minus 31.18 feet per second square. So now let's find the transverse acceleration. I can plug these all values here, which will be my r theta dot square equals to minus here this value r double dot value minus 31.18 feet per second square minus this value r 3.464 with the radius 1.5 square equals to minus 38.97 feet per second square. So I can have my r theta double dot, which is 0, plus 2 r dot theta equals to 0 plus 2 this r dot value into here minus 6, and with the radius 1.5 equals to minus 18 feet per second square. So now I have my transverse acceleration. Now we can find the magnitude. Magnitude is represented by root under ar square plus e theta square equals to this minus 38.97 feet per square plus minus 18 square, which is 42.9 feet per second square. So the magnitude of this given image is 42.9 feet per second square. The traverse acceleration of this image is I have my minus 38.97 feet per square and minus 18 feet per second square. Thank you for watching this video. I hope I was able to convey you some important subtopics regarding to this curvilinear motion, and I hope you will be solving some more problems related to this section.